Hello and welcome to our session where we'll be talking about the real-time data infrastructure platform that we built at Uber. A quick note about the authors. Hi, I'm Chinmay Soman, currently an engineer in Startree, which is a company around real-time analytics. Previously, I was part of the streaming platform team at Uber, and I'm also a committer on open source projects such as Pinot and Samza.
Hi, I'm Yupeng. I'm a software engineer at Uber. I lead the real-time data infrastructure. I'm also a committer of several open source projects.
So today I will begin by discussing the real-time analytical use cases and scalability challenges at Uber that motivated us to build a specialized real-time platform. I'll also talk about the different layers of abstraction of this platform. Next, Yupeng will discuss in detail the components chosen for each of these layers and the unique contributions made by Uber for each of these components. Finally, I'll talk about the different production challenges we addressed in Uber's multi-region ecosystem and conclude with lessons learned. So there are several use cases within Uber that need real-time data analysis, and they can be categorized across these four. They can be grouped across these four categories as shown here. For example, surge pricing is an application that computes the dynamic price of a trip by processing several demand and supply related data in real time. Similarly, Restaurant Manager is a dashboard which is used by restaurant owners across the globe to get insights into customer satisfaction, sales, inventory, and so on. It's important to note that each of these use cases has a unique set of requirements, which can often be competing in nature. And you can refer to the paper for a full set of requirements. Our platform was designed to address the following scalability challenges within Uber. The graph on the right shows the rapid increase in Uber trips over the years, which translates to an exponential growth in data that's being ingested. As of December 2020, we were getting trillions of events in any given day, which amounts to several petabytes of data. In addition, Uber keeps adding new lines of business over the years, which leads to a wide variety of use cases being onboarded onto the platform. And they can all have diverse set of requirements, as I mentioned before. And finally, the platform has to support a large user base consisting of engineers, data scientists, operators, PMs, and execs with a wide variety of skill sets, which makes it even more challenging. In order to accommodate a wide spectrum of these requirements, we came up with a layered model of our platform. At the lowest level of this abstraction is a storage layer, which provides blob storage interface with read after write guarantees. Next is streaming, which provides a pub sub interface with at least once guarantees. We need a compute layer, which can work with both storage and stream, and again provides at least one semantics. We need an OLAP or online analytical processing layer to support high QPS, low latency analytical queries. In addition, we need a SQL layer for ease of use and query flexibility, which can work with both compute and OLAP. We also need a programming API layer for advanced users. And finally, we need a metadata layer for all these other layers. This abstraction model gives us the flexibility to choose the most efficient strategy for solving any given problem. At Uber, we have adopted open source in a big way. And in the next section, Yupeng will discuss some of the key open source technologies used in some of these layers. Over to you.
Thanks, Chinmay. So first, let's look at the streaming data where Uber adopted Apache Kafka. Today, Kafka is kind of the de facto standard for data streaming and is widely adopted in the industry. It's kind of straightforward choice for Uber to take it and have been used by Uber for multiple use cases. In fact, Uber has one of the largest Kafka deployment in the world. You can see from these numbers on this slide, there are like trillions messages or PBS data flow into Kafka today. Because of this large scale and the different scaling challenges we talked about in the beginning, there are multiple innovations from Uber made to Kafka. So the first one we call this the cluster federation. So because of different use cases, we have multiple different physical clusters. And each category of clusters have its own configurations and purpose for this particular use case. For example, some for lossless guarantee, others for high throughput setup. But to simplify the discovery for the users, we have this concept of logical cluster and physical cluster differences. So that when the user wants to discover a Kafka cluster, they only need to provide the topic type information. And the routing layer built by the Kafka platform will navigate them to the right cluster. So in addition to the simplification of discovery, there are also scaling benefits from this setup. For example, we can scale like one logical type of clusters horizontally by adding more clusters. And in addition to that, we can also tolerate a single cluster failure by routing them to another. So please check out the Kafka Summit talk we had at the link in the bottom to other details in this. You also will more than welcome to check out the details in the paper. The next innovation we call this the dead letter queue, DLQ. So this is also a layer built on top of Kafka protocol. So with the open source Kafka, the consumers will process the events from the Kafka topic. And when there are like certain messages cannot be processed, for example, there's like data corruption, there are two choices by the consumers. Either they can discard this event, or they will block on this event and keep processing. However, in certain scenarios, where neither of this is sufficient, like for example, in the some payment like system, we do not want to lose any events because not processing some event may mean like the driver may not get paid. However, we also do not want to keep blocking on this message because we keep on processing these important events. So to accommodate this challenge, we build this DLQ layer by using multiple Kafka topics. As you can see on the diagram on the right, from original topics, when the message cannot be processed, if you retry multiple times through the retry topic, if they still cannot be processed, it will be published into a DLQ topic. And later on, the engineers or PM can look into this DLQ topic to figure out what happened to them, and they may choose to reprocess this with another pipeline. There's a Uber Eng blog at the bottom of this slide. You can learn about this kind of reliable reprocessing. Another innovation from the Kafka platform is called consumer proxy. This is also a pretty nice innovation because this addresses pretty important scaling challenges. So with hundreds and thousands of clients and applications at Uber, it's common and challenging to do the debugging for the applications and users. So by taking this pain, the team built a proxy layer in the middle to simplify the clients on the application layer and to encapsulate the complexities, and in addition to build enhancement to the processing. For example, the DLQ feature I talked about in the previous slide is implementing this proxy layer. Also importantly, this takes the complexity away from the Kafka clients in the application and provide a central management so that when there are new versions to be upgraded or there's new features added, we can simply upgrade the proxy layer without disrupting the clients, the user applications. Next, we are talking about the use of Apache Flink for streaming processing. So similar to Kafka, Flink is also quite well established in the industry for streaming processing. It's known for good throughput, low latency, and provides strong fault tolerance guarantees. But look at this number, you can see Uber also has a quite large deployments of Flink in the industry. There are two modes provided by the Uber teams on the Flink jobs. One is called Flink as a service, which provides an API, so people can use this API to compose the Flink jobs. The other is called like Flink SQL, where people write a SQL query to describe the business logic in a declarative way. And the team will provide the self-managed platform for this. So I want to highlight that the Flink SQL is actually built by Uber and contribute back to the Flink community. As you can see on this diagram, there are different components like query planner, optimizer, and certain other things about the deployments to build on top of the Flink libraries. So this simplifies the code generation and the ease of the job description. So you can check out the blog at the bottom link on this slide to learn more about this. Because of these two different type of deployments, we build a unified platform to centralize certain management and operation complexity. Like for example, the job validation, job monitoring, and the cluster management are all done in a central way to simplify the on-call engineers and the Flink team to operate these jobs. This is also pretty important to address the scaling challenges that we have for a small team to manage a large scale of jobs and deployments. Next, I'm going to talk about how Apache Pinode is adopted by Uber for real-time OLAP engine. So Uber chose Pinode mainly because of its pretty strong support on high QPS and low latency on the query support. In addition, it's pretty cost-effective as we did a pretty comprehensive analysis comparing to other frameworks. You can check out this comparison in detail in the paper. And Pinode is also used by Uber to empower multiple mission-critical use cases. Like for example, the restaurant manager that Chimay talked about in the beginning built on top of Pinode. And there are also certain important operation intelligence applications are using that. Pinode also had pretty good deployments inside Uber, as you can tell from the numbers on this slide. So Uber made pretty good investment on Apache Pinode, and there are certain important features that contribute by Uber to the open source project. And Upsert is a pretty good example. To our knowledge, Pinode is the first real-time OLAP engine that provides Upsert support. This is a pretty challenging problem to solve because in the real-time distributed systems, it's common for the ingested data to be modeled as a mutable files or segments for the ease of storage. And to enable Upsert, we have to be able to derive the character view from this modification logs. And we solve this problem in a quite innovative way that by partitioning the data and segments, we build a shared nothing architecture so that we can solve the Upsert problem in a very efficient way with very low overhead. And the power of the Upsert can be shown in this dashboard here. As you can see, to show the current status of the live Uber Eats orders, this can be simply described by a single SQL query on the left-hand side to show the current status. You can check out the video below to learn more about the Upsert details and its status. Another interesting innovation from Uber is to marry Presto with Pinode. Presto is known for its good SQL feature support, and it's kind of like SQL layer on top of any kind of like query engines or data sources. And Pinode is known for its good query latency as well as data freshness. So by putting this together, our users can use Presto query syntax to query P-Node and get the best from these tools. You can check out the engineering blog at the bottom. As you can see, we talk about the different building blocks of the technologies. It's still pretty important, and there are more challenges to put all this into a production. The next Qingwei will talk about some of production like learnings on this front. Back to Qingwei.
Thanks, Lord Yupeng. So as business continuity is an important goal for Uber, and therefore we have adopted a multi-region all-active strategy. And Apache Kafka forms a backbone of this strategy. So in each major Uber region, we maintain a copy of Kafka data from all other regions to form a global view of Kafka. For applications that need, high availability like Surge, we use an active-active configuration where the same application is running in these major regions simultaneously, consuming from the global Kafka. Actually, go back. So the trade-off is the computation here is expensive because it's being redundantly performed in multiple regions. However, the failover becomes quite easy. Next slide. Whereas for applications that need a high degree of consistency, we use an active-passive configuration where the application is running in only one major region at any given time. During failover, the application can just move to the surviving region and resume processing. And to assist this mode, we have invested in a mechanism for synchronizing Kafka offsets across all such regions. Next slide. Another major problem we had to address was the need for backfilling data, which is used for a variety of reasons. For example, bootstrapping table with historical data, or data correction or reprocessing. Next slide. We leverage our HDFS-based data lake for doing such backfill. In case of Kafka, the raw data is simply replayed back into Kafka. In case of Pinot, we build the Pinot segments from the raw data using a separate compute job, and then copy the segments over into Pinot once they're ready. And for Flink, there are two modes of backfill. The SQL-based mode, we translate the same SQL query into a Flink batch job. And then for the Kappa Plus mode allows us to use the same Flink API on a different data source, example, Hive instead of Kafka. You can find more details in the paper. So our platform has been running reliably in production for several years, and these are some of the lessons learned in the process. Open source has been crucial for reducing overall time to market for our products and give us a large community support. However, we had to add a lot of extensions to each of these open source technologies, as Yupeng mentioned. For example, handling multi-language, custom proprietary security mechanisms, proprietary clustering, networking infrastructure, and so on. We realized early on that enforcing standardization pays a lot in the long run. For example, Kafka is a standard interface for all logs and events in Uber. Similarly, Uber's monorepo helped us perform large migrations seamlessly and identify breaking changes early on. We also invested in a lot of operational tooling, specifically around cluster turn up, turn down, node replacement, and so on. And similar tooling for automated dashboards and alerts for new use cases. And finally, we added a lot of investment in tooling around data discovery, auditing, and self-service onboarding. And all these things helped us address each of the scalability challenges mentioned before and support using a very small engineering team. Next slide. The platform has been a result of multi-year effort from several teams, and we would like to thank all the engineers, PMs, and leaders involved in the process. Thanks a lot. And thanks again for listening to our talk, and we look forward to the questions.